Good day. My name is Samuel Ayakosho. I'm from the American University in Cairo. My research area is in robotics and control. I'll be presenting the paper titled Data-Driven Modeling of a Tooling Flexible Manipulator. The second author is Dr. Maki Abib. Here is my presentation outline. I will talk about the potential and applications of tooling flexible manipulators and its challenges. My talk will also include the related works on tooling flexible manipulator modeling and data-driven modeling, and I'll be talking about linear data-driven model development. Model comparison will be done, and I will finish with conclusion. Introduction. Recently, research inclination is moving towards the development of flexible manipulators, as rigid manipulators possess high inertia and a vast amount of energy is needed to operate them. This figure is showing flexible manipulators. It could be flexible joint manipulators or flexible link manipulators, but our focus is here. The applications of tooling flexible manipulator include application in space, construction, and medical field. And the advantages are mentioned here: lightweight or steadiness of links, low energy consumption by the system actuators, high operational speed, transportability, maneuverability, and less overall cost. But the challenges of tooling flexible manipulator is this. Uh, It has a complex and high coupled dynamics due to the elasticity introduced by the links. Nevertheless, a few number of theoretical modeling methods have been developed for this system in the available literature. This figure is showing the analytical methods that are available: the AMM, FEM, FDM, LPM, and OFM model, as well as system identification, which is sometimes called data-driven or intelligent modeling. Assume mode method. In assume mode method, the infinite dimensional model of a flexible manipulator is truncated to a finite dimensional model. The advantage of AMM over other methods is that it gives low order model, which can be easily used for control design. And the drawbacks are finding the modes for cross-section with non-regular shape is difficult. And when payload is added to the system, the dynamics differ from that of assume mode. Finite element method and finite difference method. Both are numerical techniques. And the drawbacks of FEM are as follows. FEM gives large state space model when compared with AMM. And the generated model cannot be used for efficient control due to high computational demand. The advantage of FDM is that it requires less computational power, but the disadvantages are the inability to handle complex geometries and less accurate solutions. Non-parameter method and fractional order method. RPM is the easiest of all these techniques, but it gives an accurate result. The generated model is incapable of handling the system nonlinearity and complexity. FOM is better than RPM, and the better model than integer order modeling method, a system is demanding high accuracy and precision. Challenges of FOM include selecting the fractional value of FOM is difficult, and FOM model perform well with fractional order controllers than integer order controllers. As to system identification now, this is a method in which The model structure is constructed from experimental data of its input and output. Data system identification can be classified into parametric, non-parametric, online versus offline. The drawbacks of data-driven modeling is that data-driven models require quality data. Data-driven models lack flexibility when slight changes are made to the physical system. Now we'll be talking about the research achievement and open areas. The research achievement on the modeling of flexible manipulator is the development of complex mathematical models such as AMM, FDM, and FEM. AMM is the most used approach, is widely used, and is better in approximating the complex behavior of the system compared to LPM. At the same time, there are open research areas, and the first is that the need to develop linear and non-linear data-driven model to accurately identify the system dynamics and to avoid complex mathematical equations that arises through AMM, FDM, and FEM. And the second is the need to compare the dynamic behavior of different models of a two-link flexible manipulator with the physical system. Now we'll be talking about data-driven modeling of a two-link flexible manipulator. Basically, what we do in data-driven modeling is to build relationship between the input and output data of a system. The procedure for identifying a system is as follows: acquiring the input-output data experimentally, selecting model structure, model estimation using the acquired data, and model validation. Here I'm showing the linear data-driven process. It starts with getting experimental data. Data is then divided into estimation and validation data. Then state space model structure is selected. Model estimation is done using M4seed, which is having least square algorithm embedded in it. Also, we perform model validation, and if the validation error is acceptable, then we get our model. But if not, we have to iterate this process by starting with the experiment all over again using another type of input. And they usually call this the design of experiment so as to excite the system in getting rich data from the system. For the nonlinear data-driven modeling process, we start with experimental data as well, then NAS model structure is used, and this is called neural network auto-regressive with exogenous input. And we perform the estimation and validation, and if the error is acceptable, I mean the validation error, then we get our model. If not, we have to go back again to the iterative process. Now to the linear data-driven model development. First, we are to acquire input and output data. We analyze the system as two single source systems. This figure is showing each subsystem. This is subsystem 1 and this is subsystem 2. And we are calling the experiment for subsystem 1 open loop experiment 1. And this figure is showing that input 1 is active during the experiment 1, and here input 2 is active. A bang signal was used, and it switches between 0 and a range of input values. For experiment 1, the range will be from 0.1 to 1.0, and for experiment 2, it will be from 0.1 to 1.2. And these values are based on the maximum inputs that our physical system can take. Here I'm showing a typical example of the signal we used, and the duration for the signal is 40 seconds and the sampling time is 0.002 seconds. So this is the signal here, and the model structure is a state space model structure, and this was selected because we are dealing with a CMOS system. And to model estimation, the acquired data was prepared and split into estimation and validation data. Then the estimation data was used with ENFOSID algorithm in estimating ABC and D matrices of the model. And this is showing the criteria of the estimation, the fit, the final prediction error, and the mean square error. Linear data-driven model results. So this is showing the estimated A, B, C, D, and also the K matrix, which is for the disturbance and the noise terms in the data we are using. And at the same time, this table is showing the performance indices based on the estimation. This is the fit, this is the final prediction error, and this is the mean square error. The mean square error is small, and the final prediction error is also small, and the fit, as can be seen here, is greater than 90%, except for few exceptions. We also validated the model by comparing it with the response of the validation data. We compare the response from the identified model with that of response of the validation data. And this showing a close result for the first subsystem and the second subsystem. For model comparison, we actually used AMM model, LPM model, and linear data-driven model. And we did the closed loop simulation using the same LQR for all the models, and physical system. LQR was used with the physical system, and we tried to compare the results. This is the result we got. This is link 1 angular position response. This is link 2 angular position response. This is link 1 deflection response, and this is link 2 deflection response. The models, when we look at the angular deflection response, gave a close result with the physical system. And looking at the second for link 2 angular position response, LDDM is giving a good response here compared to other models. And also for the deflection response, the LDDM model was able to capture the deflection occurring in the system, while AMM and LPM model are showing very small or a deflection that is not very visible. We also did simulation with step reference input, and this is the result for LDD model, and this is the result for the physical system. Looking at the settling time of the physical system for both links, and when we compare that with LDDM model, is so close. So meaning LDDM model is better than the other models. And by the time we look at the error too, the steady state error for LDDM model and the physical system are so close. In conclusion, the process involved in the linear and non-linear data-driven modeling of a two-link flexible manipulator was introduced in our work, and the linear data-driven model was developed. Then the closed-loop simulation result of the models, the linear data-driven model, LPM, AMM, were compared with the result of the physical system. And the results show that the linear data-driven model is better than the other models in terms of giving results that closely match that of the physical system. So in our future work, we'll be developing the non-linear data-driven model of a two-link flexible manipulator through the process we've introduced in this paper, and we shall investigate linear and non-linear control techniques that are relevant for the robust control of the system, such as model predictive control and adaptive control techniques. Thanks for listening.